Alright, so for this video, we're going to be talking about Euler, the improved Euler method, and the Runge-Kutta method. Again, they're all ways of solving a differential equation numerically. So we're going to have one. What I'm going to do is I'm going to put in some random equation here. I don't really care what it is. In this case, of course, this is a... Actually, you know what I'm going to do? I think I want to do this one. Sure. And we know that, let's say x of 0, let's say is 2. Okay. Well, we know this sucker is linear, so we could go ahead and run through that real fast, the derivation of this solution. All right. And so we could always do it by hand this way. And now remember, that won't always be true of every one we do. Okay, but this will give us a nice baseline to see what we want. And what we're going to say is we'd like to know what is x of, let's say, 4, for instance. That is the goal we seek. Okay, so remember, this right here is part of your integrating factor. So that's e to the negative 3t. So when I multiply that through by everybody, I end up with e to the negative 3t dx dt minus 3 e to the negative 3t x equals 5t e to the negative 3t. Integrate. Of course, this side just becomes e to the negative 3t times x. The other side, you're not so sure. You're like, geez, can I please do integration by parts? Okay, if you want to, but I'm going to use my calculator. Okay, so I'm going to integrate, and it's e to the negative 3t times 5 times t, comma t, I think. Isn't that what it was? 5t e to the negative 3t. That'll do it. Boom. So it comes out to be that mess right there. Now let me pop up my... Oops. All right then. So yeah, I guess I'll just write like that. Negative 5/9. 3t plus 1 e to the negative 3t. Don't forget your plus a constant. So when you divide by e to the negative 3t, to solve this sucker, you will realize you'll get x of t is equal to, okay, those guys cancel out and you get just this linear piece here. And this piece is exponential. Okay. And then at 0 we said it was equal to 2. So 2 is equal to, this piece here will cancel out, so you get a 1, so that's going to be negative 5/9. And of course e to the 0 is 1, so plus c. So c is 2 5/9, which is 23/9. So this is our answer. Okay. Oops, not negative, stupid. 3t. Okay, so I literally just typed it in. That's what it actually is. That's my answer there. Now what I'm going to do with that, of course, is grab it and go such that t equals 4. Of course, it gives me this stupid answer. So remember, if you want the actual or an approximated value, diamond, enter. So we're looking at 415,928. So 415,928. 0.911. Okay, so that's going to be our baseline. That is the actual value. Now, if you take a whole class in numerical methods, what you'll find, of course, is that you can study how much of an error that is when we do these. You can find out how much error you're going to be off by, whether we use Euler's or the Runge-Kutta number 4 method or whatever method you're using. We're not really going to get into that in this class. We're just going to talk about some of the cool ways you can do these numerically. So, way number 1 we talked about last time was the Euler method. And every single one of these is basically based on the same principle, y equals mx plus b. The idea being is you were told that some value is here, and you were told some initial slope. So you're going to go out here some step. This is a delta x, if you will. And then, of course, we're going to go up some delta y. And we are going to be at some new value, right? This is some new y. And then we're going to do it again, because then, of course, we've got some new slope, right? And then we're going to go over some delta x again and some delta y. It's always going to be that same thing. So we've done this in Excel once before with regular Euler method. So we'll start with that one, just again give us a baseline. What I want to do is I want to talk about, well, suppose we use the exact same step size for all of them, and then, oops, yes, and then I want dx dt, and so then we can compare them. The idea here is that for the same step, you're going to get a better answer as we go along. So again, we were given 0, 2 is our initial condition. And our function is equals, now remember our function was equals 3, I think it was 3 times t plus, what was it, 5? No, it was 3. Oh, for God's sakes, just read, look what you did. All right, let's try that again. So our function was 3x plus 5t. Okay, now I got it. It was 3x plus 5t. Bam. Cool. And let's just choose a generic step size. I'm going to go 0.01. So remember here, so the next the next t value we get to will be this plus, and then again it's the $, d $2 to lock it in, that guy. The next x will be, well, the previous x, that's our b, quote unquote, of the y equals mx plus b, that's our b value, plus the slope times the step. And again, don't forget you want to have the $signs there, because we're going to keep using that same d2. Hit enter. Drag this feller down. Grab all 3 of them, and we take off running. Oops, not like that, stupid. Oh, come on, this is making me mad. Come on, there you go. And we're going to drag this sucker down to about 402 or something. I think you'll find that was where we will find t equals 4. Now, in Euler's, it'll give you a pretty good approximation for the most part. Get you in a ballpark. You can be like, oh, yeah, I feel like this is probably a good answer. As you can see, wow, 348,631. 348,641. This is real. This is regular Euler's. Yuck. That is disgusting. But again, it's disgusting, friends, because you have an e to the 3t. This sucker has some serious get up in it, okay? And when you are trying to approximate this bendy thingy with a straight line, you are not going to be doing a good job. Not very good at all, okay? So the better version goes like this. Suppose you have a function, and it starts at some x naught, y naught, and you get some initial slope, which of course is dy. Well, I shouldn't say x naught, y naught. Let's do t and y, I guess. So some dy dt or dx dt. I guess I'm using x's. I'm going to go all x's. Sorry about that, you perfectionistic types. We're going to evaluate this slope at x naught, y naught. Okay, we're going to find a slope, the initial slope. Now, the Euler method says, hey, you're just going to use this here, even though the function might actually be doing this. You're only going to use the slope at the front end of the thing, which is obviously not a great idea. So what improved Euler says is this. You are going to use this guy here and this guy here to find a new y value. So this, of course, will be t naught plus the step, right? Comma. And now, what's it always been? Well, it's always been some. It's just always been y. You know, the new y value. I'll call it y1. But it's this. This is the y from Euler. Then you're going to take these 2 points and you're going to make a new slope. Okay? That is a dx dt of these points. Okay? And then you're going to average these two. And this is your new m. Then you predict the new value of y from this guy. But again, the obvious idea is this. Here you're going to have a new slope. The new slope might be like that. So if I average this slope and this slope, I'm going to get a slope that is more like, I don't know, more like that. And that might give me a more reasonable approximation for my new y. Okay? So what that's going to do for me in Excel is, well, it's not going to make it very hard at all. I'm just going to go to a new sheet here. And so I guess I'll name these. So when I'm going to put this up for you so you can play with it at home. I mean, I would play with it at home right now. I would strongly encourage that. But you do what you want to do. And I would probably call this one new or improved Euler is what they call it. No one really uses this one in the real world as far as I know. Runge-Kutta gets all the glory. But this one, you know, it pushes us in the idea of, well, how can we make it better? All right, so this is like a first step on the way to making something better. So again, I'm going to start at my initial values, 0 and 2. And my equation is still the exact same equation. So my new equation here for this guy is what it was previously. It equals 3x plus 5y. Oops. Plus 5 times y, or times t rather, like that. Okay, and what I'm going to do is I'm going to move this step over here out of the way a little further. So I'm just going to move it, I think maybe one more spot over. I haven't really decided where I want it yet. Get rid of that for right now. So what I'm going to do here is I'm going to do an intermediary y. X value. It's the one that we're going to find after we use Euler to predict it. This number right here, oopsie daisy, this number right here will be the same number we had in the very first, right here last time. Okay? And then we're going to find here a new slope. And then, of course, over here we're going to find the average slope. Now, there's nothing magical about the way I set this up. So, if you set them up slightly different than me, that's totally fine. Nobody cares. You'll be good to go. Okay? So, here, this equation is going to be exactly the same as it was before. Plus, and then $sign. But where did I have it? $G, I guess this time, $2. Okay? Now, right here is where I'm going to do what I did there last time. So it's going to be equals the the previous amount plus the slope rather, times the step. Okay? And so what I've got here is I've got that intermediate x value, which you'll notice is the same as what we had right there. That didn't change. But what it's going to change is what I do with it. So here's my new slope. My new slope is going to be equals, and again it's 3 times x, or no, 3t? Oh gosh darn it, I can't remember what I was doing. Escape. What was it? No, stop. So it's 3x plus 5t. Yeah. So equals 3x plus 5 times t. Oh, except, J, you idiot. That should have been a d. Because I want to use my new x value. See? So it's the same exact equation, but you're going to use the new x with it. Same t value, because it's the same t value, but you can use this new x value. Now, I'm going to average these guys. Now, you can do the equals average button if you like. I find it just as easy to do this. Plus this divided by 2. And that's my new average slope. So then here, it's simply going to be equals the previous amount plus the slope, but it's this average slope, right, times the step, which is again in $G, $2. Okay? So this piece will be the same. So I drag him down. This piece will be the same. If you're not sure what it is, look at this. So it's using those two. Look at this down here. It's using those two, right? Right. This column right here is the same column that you had in Euler, right here. But those become our intermediate x values this time. Our new slope is the same dealio, and of course the average. I'm still going to average those two. All right, now I could have done those all at once, but I just wanted you to see that I should probably double check all those as I go along. All right, so there they are, and I'm going to drag this sucker down, and again all the way to 400 and what, 2, I guess, because I want to predict for when x or when t is equal to 4. Whoa, Betsy, come back. Voila. Oh, nice. 426,272. 426,272. Okay? This is improved Euler. Clearly that is way better. I can live with that. I mean, you're thinking, geez, you're off by 11,000. But if you're upset about that, then I think you should become a school district administrator or some such. Because you're off by 2.5%, and I don't care. Okay? Now, I do care if you're talking about things like, again, plutonium or something. I really, really, really care. I'm not sure I care that much. It's certainly a giant improvement over that mess. Okay? That was terrible. Now, the next one, the Runge-Kutta Method, it's not hard to understand. It's hard to look at a book and understand what it's saying because, my gosh, it's tough. The way they quote unquote explain it, you're just like, wow, thanks for that explanation, dog. That was cool. And so what they do is you're going to have 4 slopes rather. So 4 different slopes, which we will then average. I say average. It's actually a weighted average. So it's a weighted average. We'll talk about that in a minute. Okay? But we're going to average them. So the book refers to them as Ks, which I find annoying. I like to think of them as M's myself. They're slopes. Okay? So the first one, K1, is regular Euler slope. Okay? It is that idea of when you are here and you took this first initial slope, it's based on x naught, y naught. Okay? And so the way the book writes it is they say, all right, well, so your dx dt is some function of, t and x, right? So this is just f of t naught x naught. That's the exact same one that we've been using for our regular Euler slope. I will write it like this right here. It's just t naught x naught. Okay? K2 should look vaguely familiar too. Okay? Well, sort of. It's similar. It's a little different in that I will write what they write up there for you, and then you can kind of see what's up. Now, when I say this t naught x naught, that's not really fair. That's based on this guy right here. Now, when we get over to the other side, it's going to be a skosh different. So I should write this. Your book actually write it as this. But what I mean by that is this. It's when I said 0, I mean it's of the initial value on this piece right here. Okay? And now, here is one step size. Okay, so our step that we've been doing is from here to here. Now, we know that our function is probably doing some other goofy thing, but we're going on a straight line from here to our step, for which for us has been 0.01 recently. Okay? Now, what the book does, they call this step size h. Okay? So the next k is written like this. See what you think about it. It is t sub n plus 1/2 h. In other words, we're going halfway across. We're going halfway out. That's half of an h. Okay? And what we're going to find is that we're going to get this guy right here. We're going to get yn, that is the not yn, xn, that is the previous value we started at, plus, check this out, this is pretty exciting, k1, which is regular Euler slope, times this step. Okay? And I like to write it like this because it gives us the form of, that's our m, there's our b rather, right? That's where we started from. Here's our slope, our m, and then here's our x, right? Which is our step size. We just went halfway out. So what are we saying? We're coming out here, we're following out to here, and we're predicting for a new value of y right there. Okay? That's pretty cool, man. Because if we predict for that value of y, okay, so what we said was we took this guy here, the original, and we predicted for a y out here. So this is some new value right here. This is t sub n plus a half of an h, comma, x sub n plus k1 times half of an h. That's some new y, x and y value. Are you with me? Cool. So what we're going to do is we're going to find the slope at that point right there. And that's going to be our second slope. Now K3 is going to be very similar. So this is where it's kind of fun. At first you're going to say, oh, this looks very familiar. The first part is always the same. Okay, for this piece right here. These two share that. In other words, we're out here in the middle again. Okay? But here's where it's pretty cool, because now what we're going to say is we're going to go like this. And this portion right here is basically improved Euler estimate, like we just did. Because what you said was, for the second piece of it, because what you said was, okay, I'll predict a value right here, okay? And so I predicted some value right there at that point. And so then what I'm going to say is I'm just going to then use my new slope to find the slope based on that piece, okay? So this was the slope at the far end. It's the slope at the far end. And then I said, okay, we'll go back to the original xn piece and use that new slope. It's going to put us somewhere else a little bit. And then K4 is exactly what a person would think it would be. It is T sub n plus h. That is, you're going all the way across. Okay? And I'm going to write plus h. I'm going to write it like that because it's the idea that you're going a full step. Okay, the book writes it a little bit different than that. I find it a little obnoxious, to be quite honest with you. But it's going to be xn plus k3, but times the full step size. Okay? Which means we're going to have 1, 2, 3, 4 slopes in Excel. We're going to have 3, 4 columns for that. And then we're going to have k. And what k is actually 1/6 k1 plus 2 k2 plus 2 k3 plus k4. And what's going to happen here is you are weighting these middle two with more weight. Okay? And then, so obviously those are doing more of the telling of what's going on. The end two slopes, not as much. So then this new k right here, this fella, comes down, and then lo and behold, you end up with this. So the new xn is going to be xn plus k times the slope. That's how I'm going to get to my next value. Okay? Which looks like y equals, again, there's your b, there's your m, and there's your x. Okay? So as we do this, kind of keep those in mind. They're not very hard to do, but what we're saying is we're saying, all right, there's our original Euler. The second one is basically the improved Euler slope. Okay? And before, we didn't use that improved Euler slope to go another step, because we could have used that improved Euler slope to predict for another intermediate x value. Okay? And then from that intermediate x value, you then could go on again. That's all we're doing here. It's really straightforward kind of a deal. Okay? So, here, let's try this here then. Let's do this. Let's say, yeah. Let's go to Excel and make it happen, I guess. So, I will say that this one's a little tedious to get set up. That is why when you're using MATLAB or Maple or any program of such nature like that, what you will find is that those programs have this functionality built in. Okay, so that's why I'm going to show it to you, but we're not going to go nuts on this stuff. Yeah, it's not a big deal for us. So I'm going to write dx dt, but I'm really going to say equals k1. Okay. Oops, and then I'm going to do k2 right here, and then k3, and then k4, and then over here I'm going to do average k, and then our step size. Now what you'll notice is I didn't do an intermediary step this time. You'll notice that last time I did this intermediate value of x, this intermediary value. I didn't have to do that. I could have gotten away from it, to be quite honest with you, right here. I didn't have to make that right here. I could have just put a parentheses around this god-awful mess like this, right? I didn't need it right there. But that formula in the parentheses, you see that right there? That is my new x value, okay? So that when I come over here to this fella, whatever was where d was right there, I could have typed in the slope that's actually in d. Okay, I could have typed in that actual equation, which was parentheses, and it was 3 times, okay, x plus 5 times t parentheses. And what you'll see is what's in that parentheses right there, that is what is in d right now. You see that? So it'll be the same answer. Well, I said it was. Did I not do that right? I might have typed it in funny. Alright, let's try that again. Escape. Oh no. No. Oh, I know why. Because I didn't. Okay, never mind. I know what I did wrong. So don't pay attention to what I'm doing. Yeah, so what goes right there is it should have been this previous x value. Sorry about that. I wasn't paying attention to what I was doing. Plus my slope, which was this fella, in that case, times, $G, $2. Yay, there it is. But again, what's in that parentheses right there is what's in column D. So I don't really have to have a column D. If you like it, it's cool. It's just, I don't know, it's just something else to keep track of, and I don't really need anything more to keep track of. This spreadsheet's going to get ugly no matter how you do it. So we'd like to keep it as pretty as possible. Now, one could see where after a person got this figured out, it might behoove a person to, come over off to the side somewhere where you can type in some values. The problem is each of these slope deals are going to change because the functions are going to end up changing every time. Okay, so just be aware of that. They're going to change a little bit. So it's not like you can very easily in Excel keep track of all this stuff and go, oh yeah, I can somehow cheat it out. It's not going to really work that easily. So then equals that guy plus $H, $2. Okay. Now remember our function, it's the same function. By the way, any function will work for this. That's not a problem, okay? But the function that we are using right now, just so that we have a baseline comparison, is 3 times x plus 5 times t. Oh, not t, you dummy. God, you dummy. Click on it. There you go. Ta-da! Now, if you come back over here to our picture here, all right, so we want to then notice that we're saying we want to take the t value plus half a step. Okay, so let's come over and see if we can make this happen. Oops. So right here, we're going to say, so if you want to think of it this way, I'm going to start building my formula here. I'm going to start doing this. So I'm going to go equals parentheses. I'm going to say this t value plus half a step and then of course $H, $2, right? And here I'm gonna get rid of this. I don't want to use this as a formula right now. I'll put the equals in front of it later. Okay, so that's my x, right? So that's my new t value. Are you with me? That's my new t value. So wherever in this column I'm using t, you see that? I'm going to use this fella instead. Okay? All right, and what would my new y value be? So my new y value, I guess I'll put a comma so you can kind of tell them apart. Not new y, I mean my new x value. My new x value will be this guy. Oh, fart. I forgot I wasn't making a formula. It'll be B2, that's my previous amount, plus half, well, so I should say plus the slope, which is C1, times 0.5 times $H $2. Okay? So that will be, those will be my t value and my x value. So when I go to build this guy right here, I'm going to use those values as my x's and y's. So the formula is, my slope is, so my formula is 3 times x, right? That's my formula. Well, what is my x? Well, it's B2 plus C1 times 0.5 times $H $2. Right? So that's 3x plus 5t, so 5 times t, which of course is this A2, plus half the step size. Got it? Uh-oh. What are you upset about, crazy person? Oh, yeah, you can't multiply times the value, can you? Sorry about that. My bad. Sorry about that. This should have been a C. Okay, we'll fix that. That should have been a C2 right there. Now notice how that's pretty close to what it was on the previous Euler one, right? It's pretty close. It's not the exact same one. It's similar because why? Because we didn't go all the way across the step, yes? We went halfway across the step. This 6.18 is what would happen if we went all the way across the step. But it's the same basic premise. In other words, what we're doing is we're basically taking half of a step and playing Euler on that half a step deal. Okay? Now, if you look at K3, K3 uses the exact same x value. Yes, it's that A2 plus 0.5, H2 and all that bit. Okay? But how is that going to be different for a y? So let's go look at it over here. Okay, so for K2, this is the same. Okay? But we're going to be using a new value, okay, for our y value, or for our x value rather. And so what it's going to look like is I'm going to copy this and paste it right down here. And what's going to happen is that in here is where things are going to shake up a little bit, okay? So this time it won't be C2, it will be D2, okay? Because we're going to use K2 for our slope this time. And everything else should be the same. Everything else is the same. And again, let's just look at that and double click. Yeah, so there it is. The only thing that changes is that guy right there. And if you go back to the previous page, you'll see that. It's K1, K2. That's the only thing that changed. Okay? So basically, I can take this guy right here, all right, and I could anyway, and copy it over. You run a risk of doing it. I'm going to go ahead and do that. And you're like, oh my gosh, what happened? Well, dude, you slid everybody over one. And that's not what you wanted to do. So what you can do is click on this guy here. Oh, click on the corner of this feller and drag, if you're good. Okay, if you're good. Okay, now I'm just mad. Okay, darn you. What I'm looking for is that cursor right. Okay, maybe. That cursor. Okay. And I want this one to be back where it was, which is there, yes? And now I want to use D2 for my slope, is that right? That is correct. So I think everything else is fine after that. Again, you run a risk by doing this because you want to be a little careful. Now there is a way around that, which I can actually show you. I want A to stay in column A. So I can use a dollar sign in front of A. And I want what's in B to stay in column B, so I can actually use a dollar sign in front of the B. Okay? And then what I can do is this, is hit enter. So then get rid of this guy. And what will happen is this. Watch what happens when I drag it over. Oops. Okay, maybe. Look what happened. When I drug it over, I wanted the C to move, so I let it move. I didn't put a dollar sign in front of the C2, and when I drug it over, it became D2. But I left those over there, and they stayed put when I drug it over, and so that's my actual answer. And yay, we're awesome. Good for us. Now, the last one is a little tricky, but not terrible. It's not horrible. So for the last one, it's going to be, well, we're going to say equals, or not equals. I'm just going to put down here my x's and y's, so my t rather. So it's going to be A2, and yeah, I'm going to use dollar signs this time, plus the step, like so. That's my t value, comma, my y value. And so my y value is going to be B2 again, right? Plus, and then this time it's going to be K3, so E3. Nope, not E3, E2 rather, right? That is K3 is an E2. But then this time times the entire step, so. Right? And so that should make it happen. And that is what K4 is. So right here, now, you could drag this one over, but I think that's annoying, so I'm not going to. I'm going to say it's equals, remember it's 3 times my x value, which is this guy. Okay, I don't need the dollar sign in front because I'm not going to drag this one. If you want to put it there, it doesn't hurt anything. And this time we're going plus the full step. Again, I need to make sure that's locked in because I'm going to drag it down in a minute, and I don't want it to change when I drag it down. And then parentheses, and then plus 5 times my x. Oh, for God's sakes! Let's try that again, stupid. Control C. Put that over there. Control V. Try to do it right this time, you clown. All right, now let's put the x in here where it belongs instead of the frickin' t. So it's going to be B2, right? Oops, what just happened? Oh yeah, B2 plus the slope, which we know the slope is in that guy right there, times the full step size, which is again $H, $2. Ta-da! Ta-da! And then here our average is equals 1/6 of this. Oops, now you gotta put times right there or it'll freak out and yell at you. Plus 2 times that. Oh, no, leave me alone. Just leave me alone, you stupid computer. Okay, that guy plus 2 times that guy plus 2 times oh, for God's sakes. Really helpful. If I wasn't not feeling good, that would make my life so much nicer. There we go. Plus that dude, parentheses. Ta-da! And I say it again. Ta-da! I'm going to move these guys out of the way. I'm going to put them over here so you can still reference them when I post this later. Just going to get them out of my face for a minute. Now I'm going to take all these dudes right here, pull them down just one, grab all these, and let's take off running with it. And we'll cross our fingers because I didn't do this ahead of time to make sure, you know, hey, I can still do this since last year. So who knows? Whee! In years past, I have done those other intermediary steps for x's or for t's and x's. I didn't want to this time. It wasn't necessary. Oh my God, you're so stupid, Jay. You're so stupid. Okay, stop. Oh my gosh. Okay. Okay, that's just embarrassing. Okay, I came home from school sick today. I didn't feel good. Don't make fun of me. All right, so Jay, the consummate idiot here, forgot to actually put in a formula. So remember, it's the previous amount plus, all right, our average slope, okay, times our step size. I know, let's just count to 402. Okay, sounds like a great idea. Wow. Whee! Oops, come back here, you hippie. 415,921. Let's see how that does. 415,921. Oh my word. And then once again, I'll say it again. If you have a problem being off by 7 out of 420,000, you should really think about getting into public school education. Because you're off, well, let's times it by 100 so we don't freak people out. Times by 100. Because you will fit right in. Look at that. You are off by 0.00166%. And you know what? I feel like that's good enough for any government contractor, okay? And there you go. You're home free. Now, what I'm going to do is give you another one problem here together. For instance, we could do dx dt. And of course, this could be dy dt. Just doesn't really matter in that regard. Hey, let's do one we've seen back in the day. So 0.02. Oh, yeah, let's do this one. 0.02x times 14 minus x or something. So we've seen this fella, right? This is a, we know this is a logistic equation, right? And let's just go ahead and bust this out for fun, I guess, just for good times. So let's just say x naught is, it's 2, I guess. I'm going to have a 2 fetish tonight. Let's do 3. All right. So if you recall, we've done this. To solve this, it's separable, of course. Okay. Dx is equal to 0.02 dt. Integrate. And again, I apologize. This video is maybe, well, actually, I don't apologize. It's pretty dadgum good quality, but I don't feel very good, so kind of losing my steam here rapidly. But I wanted to get this done for you tonight so that you could have you ready to go, be ready to tackle this stuff tomorrow. And so I end up with that thing. Now, if you recall, that's really just negative 1/14. And then I see a subtraction of logarithms, so I know that's just division. And so it's the x goes on the bottom, so it's the ln of x minus 14 over x is equal to 0.02 t plus a constant. If you multiply by 14 to both sides, you will get negative 14. You get negative 0.28 t plus a constant. Don't sweat that constant, because it's a different constant now, but it's still a constant, and it'll all come out in the wash when you're done. When you exponentiate, you get this mess. Right? Multiply by x to both sides. Subtract. Factor out. Okay. We know at 0 it's 3, so 3 is equal to 14 over 1 minus c, so 14 thirds. Why did I do that? That was just dumb. Well, I don't really care. It's fine. So 1 minus 14 thirds is equal to c. Well, that's 3 thirds. Minus 14 thirds is negative 11 thirds. So c is negative 11 thirds. So that makes this plus 11 thirds there. Okay. Anyway, that's the idea. Yeah, exactly. Exactly right. Beautiful. So then if I want to know, let's just say I want to know some value at x of, I don't know, I'm just going to do x of 2, something different this time. That's what I want to know. And so you just plug that in, see what happens. So About 4.52. 4.524. Okay. Now, coming back into Excel. Oh, one thing I could have done right off the bat too, by the way. So that's with the same step size. Obviously, if you wanted to, you could. I'm going to just for fun. You can see just how crappy it'd be different. 0.1 rather. Obviously, this thing will update. And there's 4 right there. And look at that. You're still pretty darn close, right? Because it was what, 4? What was it? I forget now. Oh, no, that's what I wanted. I forgot what I wanted. See, it's 415,000. Oh, no, actually, that's right. Yeah, you're right. Never mind, Jay. So a minute ago, I divided by 421,000. So my apologies. I should have divided by 415,000, in which case, you know, I was still off by 0.00 something percent, so nobody cares. So leave me alone. But look at this one here, 415,659. Now I'm off by like 300 instead of 7. But guess what? That's a lot better than what happens with improved Euler. Oh my. That's still off by, you know, a considerable piece. And then, but wait, you ain't seen nothing yet, friends. Watch how bad this one is. Yeah, 93,000, 92,000. That's pretty lame. Okay, so just be aware of that. Again, it matters which of these you're using. I would always, my default step size is 0.01. That's just kind of how I do things. You know, you can do what you want to do when you run a spreadsheet, but that's what I want to do. Now, right here, okay, oops, not right there. Sorry, escape. Right here is where the magic happens, yes? Because our formula this time is, 0.02 times the population times 14 minus the population, right? And so 2 things I have to do. Copy this down, so double click, voila, and change that initial condition to 3. And then come down here, we went down to 2 this time for whatever reason. I felt like doing 2. And so 4.523. Okay. Now in improved Euler, it's the same basic premise. The difference here being is I'm going to have to do, I'm going to have to tweak a few things, obviously. So I'm going to put this back to 0.01. Okay. My initial condition gets changed, so that's cool. My slope gets changed here, so it's 0.02 times this guy times parentheses 14 minus this guy parentheses, voila. Okay, double check to make sure that's right. Yep. Now my intermediate x value, that's correct. That doesn't change at all. And then this new slope, again, this is the way I have it set up. This is wrong, right? Because that needs to be this formula. It needs to be, it needs to be equals 0.02 times the new x value. Okay? Times, and then 14 minus that new x value. Okay, if you're going to do it this way. Now, hit enter there, and then I'm going to copy this one down. Did I copy this one down? I don't think I did. Voila. Now everything should be updated, and away we go. And down here at 2, we should see that we are sitting at 4.52, which is pretty good. This one, of course, is going to take a little more doing because I have to change a bunch of formulas. So my formula here is 0.02 times this times so that one's really easy to do. Now be careful on this one. If you're smart, you'll be very careful and do what I tell you on this one. Okay. This is that's my t, and I don't need the t, so I'm going to get rid of that t business. But this mess right here, that is my x value. Are you with me? So what I'm going to do is I'm just going to go 0.02 times that. Okay? Times, parentheses, 14 minus, and then I'm going to copy this thing, Control C, Control V. Voila. Booyah. That's done. I'm going to do the same thing here. I'm going to get rid of this T part because I don't need it. Okay. I'm going to change this to 0.02 times that times parentheses 14 minus, and again I'm going to copy this. Bam. Oh, for crying out loud. Oh. No, no. Fart. Apparently I didn't hit. Oh. Escape. Okay, let's try this again. Alright, get rid of this X piece. Apparently I didn't hit copy hard enough or something, or I didn't hit control hard enough. So let's try that again. 0.02 times parentheses 14 minus, again copy that, so control C, control V, bam. Notice how those three are about the same. They should be. And again, lose this portion. And then again, 0.02 times, oops, and then times 14 minus this piece. Nice. Now these four have been updated. These four. So if you paste them down by double clicking, change that to a 3, we should be good to go. Oops, I didn't update my step size apparently. Then we're going to 2, which is right there, 4.52453. I didn't remember what I wrote down. 4.524. I wish I'd bring the calculator up, I guess. The calculator has the exact value on it. The exact quote-unquote value, right? So, as you can see, we're talking about 4.524253. And you're like, can you give me more decimals? And I say, well, I'd love to. How many you want? Now, check this out. You're accurate out to at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You're out to go at 11 decimal places. Brother, if that's not good enough for you, you need to just, you need to take a pill or something. You have problems, okay? Now this one probably is okay as well. I can probably go out of ways on him. See, it's pretty good too, but it changes about what that decimal place right there where the 2 is, I think. And this one here, is pretty good too, I think. But it's only good out to like 2 decimal places. So clearly that's a better deal. Now, again, I'm going to save this spreadsheet. I will post it online for you so that you can see it and dink around with it to your heart's content. Just find a way that makes you happy. So I'll call it numerical solutions. I want you to to create your own as well. But the thing is I want you to feel comfortable with it. So play with them. And again, once you get the spreadsheet set up the way you want it to, all you have to do is change what goes where. So for instance, you want to change it so you have to change your function, of course, and then you may tweak and make things a little bit better, a little different. So hope that helps.